Action. Boom. Hello and welcome back to Calculus 3, section 11.2, vectors in 3D. Right, so everything that we learned from 2D is going to translate here, except the direction. Direction doesn't compute well and easily in these. There are certain things you can do about the direction, but there are no formulas that we are learning here regarding direction. So we are going to focus first on the 3D space, then we're going to focus on the magnitude, same properties and rules on the zero vector and everything else. The two vectors are the same, and so all of that stuff translates. They're free to move in space. So all of that will be back, and then we'll talk about some equations, extra equations of a sphere and others. So let's first start understanding the 3D coordinate system. There are a few ways to draw the coordinate system. We only have 2D surfaces in front of us, and we are supposed to portray a 3D. So we'll have to use perspective in drawing. So all of these have 90 degrees between them. Now, the way to understand this is to look at the corner of the classroom. So if you look at the upper left corner of the classroom by the speaker over there, you will find what I'm trying to draw on the screen. Now, technically the one that I actually drew is the one on the floor, but you can't see it because of the desks in a way. So the XY, or in this case, would be the floor. And the XZ, this would be where the board is. And this is the white wall over there. So that would be what we have. Now, this particular system, if you put X and Y in this order, is called right-hand system. Because when you extend your thumb in the direction of a positive Z, and you wrap your fingers around Z-axis, your fingers, as they wrap around, hit X-axis first, and then Y. So it's called the right hand because the right hand wrapping around Z hits X and then hits Y. The left hand rule would switch X and Y because as you extend your thumb in the positive Z direction, your fingers, as they wrap around Z, would hit X first. For the left, would hit X first, and then Y, right? So this coordinate system is called the right-hand system. And throughout the entire Calculus 3, that's the only one we are going to use. Now, when you go into your AutoCAD, right, you get to pick which one you want to use. Depending where you work or who you work and so on, they might use left or the right. So you have to be careful about those things. Now, this is the base for what you have maybe done in physics already with the, what is it called? Anyone? Yes, it's all for magnetic fields and stuff, so the right-hand rule, you have it there as well. Now, it's from here. Now, when you are in 2D, the two axes intersected, created 4 quadrants, right? Now, you are intersecting 3 planes. There's a ceiling, and there are 2 walls. They give rise to 8 spaces, all right? And those 8 spaces are called octets. So this one over here is the first octet when all x, y, and z are positive. So you have 8 of these. It's difficult to draw this, so I'm just going to cheat off of the image in a textbook on page 771. You can see the green plane, the blue plane, and the orange plane intersecting, creating 8 spaces. So the one that has a point is the one that it's a first octet, because that's the one that has all of the x, y, and z positive. In all others, octets, others are negative. So these are, so this is what we have for our 3D coordinate system. Now there are other ways that you can portray the coordinate system in. That would be, another one would be this. X, Y, and then Z. So we'll use this as well. This is also right coordinate system, because as you wrap around with the right hand, the fingers going around Z axis hit X first and then Y. So it's a right hand. But it's a different perspective. You can see over here Z and Y making 90 degrees. They're still making 90 degrees in here, in the other drawing, but you actually don't see the 90s. At least over here you see one at 90 degrees. So both of these are right hand, and they just have a different perspective. So we are going to use both of these. It will depend on what we have to draw and what we have to understand in order for us to well, use one or the other. Now, point in 3D has x, y, and z coordinates. And if we want to graph point 2, 3, 6, we have to do it in order of the coordinates. So we start by graphing 2 first. That's the first coordinate. So at this point, you are at 2, 0, 0. Then we are going to create a parallel line to y-axis. And that line has to have a length of 4. When you reach this location, you are at 2, oh no, not 4, 3, sorry. When you reach this location, you are at 2, 3, 0. This particular point is on the floor. 2 units in x direction and 4 units in y direction. And then you have to rise 6 units up. That's going to be parallel to z. And we'll say it's somewhere over here. 4, 2, 3, 6. So the path is go down the x-axis first, then parallel with y, and then up with z to locate your point. Clearly, if you had negative z, you would go down. If you had negative x, would be starting on the other side of the x-axis. Negative y would be going this way, and so on. So to graph a point, it's much more complicated, and you know, certain amount of OCD is very welcomed for something like this. So now we can locate our point in 3D. And that is extremely important because we see that we know the origin is 0, 0, 0. So now we see that we can connect these two and create our 3D vector U. I'm not going to do it on this graph, but we can connect initial point at 0, 0, 0 and the terminal point 2, 3, 6 to create a vector U with the spiky brackets 2, 3, 6. So at this point, we know how to locate points. Now, I already mentioned that this is your floor. We are going to come back to these analogies many times in this class because our class is 3D. All of the objects are 3D. And we need to be able to understand and see where these things are and what they look like and all of that kind of stuff. So we'll try to look for the objects and shapes around us. So now, you can use the classroom as the base for your thinking. We are going to call our floor z equals 0 because I'm going to place the origin 0, 0, 0 in that left corner on the floor, right? So as you're looking at the board in the classroom, left corner on the floor is going to be where 0, 0 is. Now, that will make the white wall x-axis, the board wall y, right? The line along the floor would be the y, and the line going up would be z. So now floor is going to be plane z equals 0, which would make your ceiling a plane z equals 10 because it's, say, 10 feet tall. So if the ceiling is at 10 feet, then the ceiling would be a plane z equals 10. Now, note that x and y are not mentioned at all in these equations of the plane. And the reason is they extend indefinitely forever in x and y directions, so that's why we don't mention them. You have seen this before in your education when you learned in algebra for the first time the equation for horizontal and vertical line. In algebra, in the xy coordinate system, if you draw a vertical line through number 2, your equation for that is x equals to 2, and the y is not mentioned at all, because y takes on all of the values from negative infinity to positive infinity. X is fixed to be 2 all the time. So it's sufficient to just write x equals to 2, and that immediately represents the vertical line. Horizontal line going through, let's say, 3 has equation y equals to 3. Again, no mention of x variable because x takes on all of the values from negative infinity to positive infinity, and y is strictly fixed to be 3 all the time. So now, when we go to our world in 3D, and I have x and a y, and we create a plane. This is our floor, and we call it z equals to 0 because the only thing that I care is how high is that horizontal plane. Now, since we decided to put the 0, 0, 0 origin in the corner of the classroom on the floor, then xy plane has equation of z equals 0. Now, at height 10, I will have another plane at height 10. And that plane at height 10 will be z equals to 10. These two planes are parallel to each other. They will never intersect. And they are separated, in the case of our classroom, by 10 feet of space. That's about 3.5 meters. So we have 10 feet in between these two planes. Now, the wall along the x-axis, which is the white wall over there. I know. So the wall along the x-axis will create a plane y equal to 0. That's our white wall. So now that we have that white wall, we can figure out, so that's our x-axis, right? We can figure out where the other wall is by simply measuring the distance between them. Now, please tell me exactly how many feet distance. How much? 26? How did you get 26? He has the right idea. Which reference? Now there is something that you can use to measure exact distance. Ceiling, thank you. Why is the ceiling the way to measure the exact distance? Yeah, because it has 2 by 2 feet square grid. All right, let's get counting and multiplying by 2. Let's go. See, these are the things, when you are sitting bored in DMV, why are you not figuring out the square footage of the building? Easy, right? So what do we have? Yeah, we'll have to estimate a little bit over there, but it's not bad. 30. There we go. Thank you. So now I will draw another wall on this side. See, I'm building a 3D classroom right now. When you combine this with the other two up there, right? You see that now you have the floor and the top and then the two sides. We just need to take care of this wall and the one in the back. So this is y equals to 30 now. Again, no need to put any x's or z's because they will be infinite. Great. So we have those parallel planes. And last one. 30 again. So we are 30, 30 by 10. Okay. The last one would be over here. And this would be your x equals to 0, which is the board wall. And then 30 away. We'll have x equals to 30. So now if you can somehow assemble these in your head, move this up, it will connect here, and then move these to the side and they will plug the sides. And you got the box. This is how you confine things. This is extremely important. Your chapter 13 will be complete disaster if you're not able to do these things. So you have to be able to stare at these images and mentally assemble the box. Now, that's nothing else but simply floor and your ceiling, the white wall and the window wall, and the two board walls. There's a board on that one as well. So we have the window and the white wall. Well, that both starts with W, so W walls. Oh no, and this is whiteboard and that's a whiteboard. Whatever. Ruined, move on. You can now find the location of every object, every student, every desk, everything in the classroom. You can find the location of it by figuring out, right, the coordinates of the point in the 3D space of where that object is. Now, how do we measure the distance? Well, in what we call Euclidean space, which is the flat space, the distance is, the shortest distance is the straight line between 2 points. That's not true on curved surfaces. We'll get there in chapter 12. But now, for now, the shortest distance between 2 points is a straight line. And the distance will be measured simply by x2 minus x1 squared plus y2 minus y1 squared. This is your distance formula from algebra. But since we are in 3D, we also need to have the z component in it. You will find that many formulas in Calculus 3 are just your old formulas recycled with z placed in the formula. So this is your distance formula. You will have 2 points in space. So distance between x1, y1, z1 and x2, y2, z2. So far we learned that basic planes, the ones that are perpendicular to xy, xz, and yz, have equations x equals y equals and z equals, right? We also learned the distance formula in the 3D space, and now we can also talk about the equation of the sphere. Well, circle is x squared plus y squared. Sphere will just add z squared to the mix. And it's equal to radius squared. So this is the sphere centered at 0, 0, 0 at the origin. The more general equation of the sphere would be x minus a squared plus y minus b squared plus z minus c squared equals r squared. Now that's the one that I want to box. This one is centered at A, B, C. So this is the equation for your basketball, right? And you know that basketball, you can move in space. So the basketball doesn't have to sit in a corner at 0, 0, 0. Basketball can be anywhere in this classroom. The location of where basketball is in this classroom is given by ABC. The size of the basketball is given by R, because that's the radius, right? The difference between baseball and the basketball is just R. They can be in the same location, right? You put the baseball here, then you remove the baseball, put the basketball in the same location, right? So that location is ABC. Now the difference between basketball and the baseball would be the size of it, which is the radius, which is R. So that's what we have. Now, I noticed also in a textbook they're talking about the internal space, right? The inside space of the sphere. And you achieve that by simply placing this symbol, like less than. And that just means the inside of the sphere. Or you can put the greater than, which is the negative space, which means everything outside of the sphere. So if you have an object which contains some liquid, like this bleach thing over here. Nice. Don't do this at home, I'm professional. I can contain this liquid inside by simply having the bounds of this object, right, with some kind of equation. We'll get there in this class. This is just a cylinder with something that looks like a cone. It's not a cone, but cylinder, cone, and then we don't care about this because the water doesn't go there unless you're spraying. So the inside of this would be the equation. We'll learn this in chapter 12, the equation for this. So if you're just looking at the cylinder here, whatever is contained inside, we can use the less than or equal than to say inside of it. Greater than or equal to for the space outside of it. And then equal. What is equal? If the less than is the space inside, greater than is the space outside, what's equal? Surface of the bottle. It's the plastic, right? It's the plastic. That's what it is. You have, like the banana peel, the thing you throw away, that's equal, right? The less than is the part that you eat, right? It's the inside. So that's that. And finally, we get to talk about vectors. Now, 3D space is denoted R3. That's notation. Vectors in R3. That's just our fancy math way to say vectors in 3D. So a vector u in 3D will be given as ABC or u1, u2, u3, whatever. You will have three components. Initial point 0, 0, 0, terminal point ABC. Zero vector will have 0, 0, 0 components. Unit vector u is still vector u divided by the magnitude. Magnitude u is a squared plus b squared plus c squared. That's the magnitude. Remember we said don't worry about the direction. We get to scale them, add, subtract, same way as in 2D. So add, subtract, scale, same as in R2. And then properties, same as in R2. So that big blue list we had, same list in 3D. You add them component-wise, you multiply. If you're scaling, you multiply each component by whatever the number is there to make it larger or smaller. So all of that stuff stays the same. We don't have any new concepts regarding that. And that's it. I hope you're not disappointed, but that's that. Now let's do one or two exercises from homework. Oh, I'm going to move this. I know you can't do this in your notebooks, but such is life. Move this here because I also want to say that this is AI plus BJ plus CK, right? I want also to add the component form with now adding vector K, unit vector K for Z direction. So just for the sake of completeness, so that all right, now let's take a look at something. Ooh, you definitely forgot this. Let's see. Find the center of the sphere. And I just want to find the most diabolical case I can. There we go. Nice. So x squared plus y squared plus z squared minus 6x plus 6y minus 8z minus 2 equal to 0. So what is the concept that we have to use?
Completing the square.
Completing the square. Good. So we group x with x, y with y, and z with z, and kick 2 to the other side. The formula for completing the square is b divided by 2 squared. So for the first one is 6 divided by 2 squared, which is 9. For the second one is also 6 divided by 2 squared. Well, I mean, yeah, it's negative 6, but square will kill it, so no one cares. And then 8 divided by 2 squared, which is 16. These are the numbers that you add and subtract inside the parenthesis to create the square of binomial. So the first parenthesis is x squared minus 6x, and then plus 9 minus 9, plus y squared plus 6y, again plus 9 minus 9. This is intermediate algebra. Plus z squared minus 8z plus 16 minus 16 equals to 2. The first three create completed square, square root of the first, sine of the second, square root of the third. Then we have plus 9 outside. Plus y plus 3 square, plus square root of the first, sine of the second, square root of the third. Oh, I forgot minus 9. Why I put plus 9 here? Minus 9. Minus 9, minus 9, plus square root of the first, sine of the second, square root of the third, squared, minus 16 equals to 2. So now I have x minus 3 squared plus y plus 3 squared plus z minus 4 squared is equal to 36, right? That's 18, 20, 36, yes. So center is at 3, negative 3, positive 4. Right, all opposite signs because the equation of the sphere has negatives in it. And the radius is 6. Six inches. So we have to do completing the square. And the formula for completing the square is b divided by 2 squared. What's up?
What was the question? I thought it said find the center of the radius.
Find the center. Yeah, I just added the radius. It's free. If you're getting a free drink with your burger, would you pass on it? Exactly. Like this. The square root of 36, right? It's r squared. Which makes me just say, right? Yeah. Now the rest is adding and subtracting coordinates, so I'll see you tomorrow.